To the third Math Thursday during Devtoberfest. My name is Nora. I'm a developer advocate, and today's session will be on the SAP HANA Cloud Multi-Model capabilities. We have Markus Fahrt with us, who's a development architect in the HANA team. But before we start with the session, I want to quickly remind everyone to please join the Devtoberfest group in the SAP community. Only that way you can be actually part of the contest. And when you're part of the contest, you can take validation tutorials of each session, and you can also be part of the fun activities and earn a lot of points. And when you reach Nerdvana, which is the highest tier, you will be part of a random drawing, and maybe you will be a winner next year. And the winners from last year, well, you will be a winner this year, but go on the prize next year. And the winners from last year actually get to go to the ASIC Tech Connect event in Florida this year. So the prize is really cool. So make sure you are part of the Devtoberfest contest and watch all the sessions, take all the validation tutorials, whatever you can get, collect as many points as possible. And with that, yeah, just enjoy today's session. I am very excited to learn more about the HANA multi-model capabilities, especially the knowledge graph I heard is part of it too. So yeah, just enjoy the session. And Markus, the floor is yours.
Yeah, thanks, and welcome also from my side to this session. Let's dive right into it. HANA Cloud provides a set of specialized capabilities like spatial engine and JSON document store, which are used to create what we call intelligent data applications. The vector engine and the machine learning capabilities, as well as the to-be-released knowledge graph engine, are used to create AI or GenAI applications or workflow. And in turn, we ourselves use GenAI technology in order to improve the HANA Cloud tooling for the developer, for data scientist, as well as for the administrator. For example, there is a natural language SQL console, which helps the developer to interact with HANA. In today's session, I will focus on the vector engine and the knowledge graph engine. So let's start off with the vector engine. It actually sounds a little bit more than it is. It basically is a SQL data type to store high-dimensional vectors. For example, those derived from text embedding functions, which convert natural language text into vectors, which is just a number, a set of numbers. Now, the magic of these text embedding functions, like from OpenAI, text embedding ADA002, is that text that is semantically similar to each other is mapped to vectors in that high-dimensional space that are close to each other. Simplified way how that works is depicted on the right-hand side, where we see the text database and table and icebreakers and the corresponding vectors in a very simplified two-dimensional vector space. Now, a semantic search with the term database simply becomes a k-nearest neighbor search in that vector space. So if I search with a vector for database, I will find the vector representing table, but I will not find the vector representing icebreaker. For k-nearest neighbor search in that high-dimensional space, HANA Cloud provides two vector functions, distance functions. One is L2 or Euclidean distance, and the other one is cosine similarity, which basically is just the angle between these vectors. So these distance functions are used to run k-nearest neighbor queries. What we also support in the vector engine is a way to index your vector data in order to speed up these queries. We'll cover that in a second. If you look from a consumption perspective, how do you touch the vector engine in HANA Cloud? Of course, there is SQL. There is, of course, our cloud application programming model, which you use to develop applications on top of the database. But there is also an integration into the LangChain library, both in Python as well as in JavaScript. So if you are active in the GenAI community, you probably heard of LangChain. One of the things that we have on the roadmap is what we call in-database text embeddings. More on that in a second. And also support for native storage extension for the vector data type. So you can spill out actually these heavy vectors into a more cost-efficient storage, but still enjoy high-performing queries. Now, the primary reason why we developed the vector engine HANA Cloud is GenAI and the retrieval augmented generation pattern, which is depicted on the right-hand side. So I'm sure you heard about it. Basically, it is about for an end-user query or end-user prompt, how do you best collect the context so that a large language model, which generates an answer, does not hallucinate when it's asked about something it doesn't know about. So semantic search, so this vector-based search is a very efficient way to retrieve context from natural language documents which match to your query, to your prompt, and this context is then added to the prompt, and the large language model can kind of read out the context and generate an answer grounded in that information provided. There is a little bit more that you can do with text embedding vectors or vectors in general. So for example, we'll see later on how clustering can work. So in order to find groups in your documents, for example, or it can be used to provide approaches for classification and outlier detection. Now, the vector engine, if you touch it on SQL, you basically work with these type of SQL syntax. So there is the real vector data type depicted on the left-hand side, which you use just like any other SQL data type in order to define your table. So on the left-hand side, you see that there is one column called vec, which is of real vector data type. So it's meant to store high-dimensional vectors. In this case, there is a constraint on the dimensionality of the vector. So you can put in vectors which do have 1536 elements, which happens to be the size of the vectors provided by OpenAI ADA-002 embedding function. For data manipulation, there is the typecast to real vector, which converts a string or an array into that internal vector data type. In order to run queries, I already mentioned the cosine similarity built-in distance function, which you see on the right-hand side, which in this case compares a query vector to all the vectors in my table and returns the most similar one. So this is the way how you run k-nearest neighbor searches in HANA using SQL. Now, if we talk about these queries and the performance, if you do nothing, you can expect to scan 1 million vectors in just about a second. So of course, this depends on the resources provided to your HANA Cloud system, but this is a rule of thumb, which is sufficient in most of the GenAI RAG scenarios, for example, where you can retrieve the top k nearest neighbors or the best matching context in a volume of, let's say, 1 million documents or chunks. In order to speed up these k-nearest neighbor queries, you can create an index, and that is new with QRC3. Which builds an index on these vector data and substantially speeds up these queries. However, these index allow you to evaluate approximate nearest neighbors. So it's not always guaranteed to find the exact nearest neighbors, but in most scenarios, this actually should be good enough. So again, also depending on your sizing and the resources and the queries and stuff like that, you can expect on large volumes of vectors to see a speed up of a factor of 100 or even 1,000. Now, of course, one of the important questions is, how do you get to text embedding vectors when you want to do semantic search, for example, in a RAG workflow? As of today, Here's one example how you could do it. So you have an application on top, be it a cup application or a workflow that leverages LangChain. You would essentially connect to BTP, to GenAI Hub, to the text embedding services exposed there on BTP. And you would convert your text into these text embedding vectors, and then you would store the text along with the embedding vector into a HANA Cloud table in order to retrieve it. So that's it as of today. What we plan to release in the next QRC of HANA Cloud is in-database text embedding. So there will be a text embedding service tightly coupled to HANA Cloud, which allows you to convert documents or natural language text or queries to text embedding vectors directly in the database. And there will be primarily two ways on how you can leverage that in-database text embedding service. One is depicted above via that built-in function vector embedding, which simply takes a string, in this case, bunch of heroes, and converts it to an embedding vector, which then can be used to search in your documents or the corresponding text embedding vectors. This is most flexible, this table function vector embedding. If you want to do batch embedding, then you probably rather look at that procedure depicted below here, which is part of the PAL predictive analysis library, PAL text embedding, which takes a table as one of its input and then converts all of the natural language text in that table into embedding vectors. And you can work with the resulting table and, for example, update your table or store it. Let's take a brief look how that looks like in the system. So what I've prepared is a table containing TV episodes. So there are roughly 800,000 TV episodes in my table. This is how the table looks like. So for example, there is information about the Star Trek episodes. And what you can do now is directly in the database, do a k-nearest neighbor search. So essentially a semantic search leveraging the text embedding that is present in that table. So I'm asking, when was Picard adopted by the Borg? And this vector embedding function converts this query into this text embedding vector, which you see down here, which I then can use in a query to evaluate the k-nearest neighbors. So this was pretty fast on 800,000 vectors. So there was a vector index behind. But basically what we do see when I query when was Picard adopted by the Borg, one of the best results is depicted down here. And if I look at the description, it says Picard is adopted by the Borg. So you see this is the kind of that similarity magic that takes place using these text embedding functions. So a nice way and a great way to simplify certain architectures in your GenAI applications. Just briefly mention a couple of variants to plain vanilla k-nearest neighbor search. One is called maximum marginal relevance. It's also a way to retrieve k-nearest neighbors. However, in this query variant, you could say you are removing duplicates or near duplicates from the result set. So if you do a k-nearest neighbor search, for example, for that blue dot on the right-hand side, the Avengers movies, you'll find Guardians of the Galaxy. You'll also find Guardians of the Galaxy Volume 2, which you probably might not want to have in your result set. So this retrieval technique, maximum marginal relevance, kind of checks upon the k-nearest neighbors by comparing them pairwise and kind of removing the near duplicates or only yielding the results that are most different from each other. Another retrieval technique, for example, in GenAI workflows is combining full text search or text search with that vector-based semantic search. This is also supported in HANA Cloud since we also have text index and keyword searches supported in HANA Cloud. So the way this would work is that you would issue a keyword search and a vector-based search in parallel, and then you kind of would fuse the results or re-rank the results in sort of a combined way. So there is no cooking recipe how that is done, which works all the time. But basically, this is, of course, available or doable on a mere SQL level. Now, a little bit more advanced is classification and clustering. So you could think about a classification approach. For example, if you look at your product descriptions or something like that, where you would simply run a k-nearest neighbor search for your kind of query description, and then evaluate, for example, the class labels and the nearest neighbors and the most similar product descriptions in order to assign a class label to your query document. So pretty straightforward. It works quite well. The other option, then it comes, for example, to clustering, is that PAL, our machine learning library in HANA Cloud, starts to support the real vector data type. So you can combine, for example, text embeddings along with other attributes, for example, in DB-scan clustering algorithm, and improve the results by taking natural language text also into account. One nice way on how you can run clustering is by using the built-in HANA Cloud Property Graph engine and its community detection algorithm. And the way this works is basically that you would run multiple k-nearest neighbor vector searches in order to derive a partial similarity matrix. So for each document, for example, in your data set, you will evaluate the top 5 nearest neighbors and store its similarity or distance. And if you look at that partial similarity matrix, you can interpret that as a network, as a graph, essentially, and then use graph engine capabilities and build in algorithms like the Louvain community detection algorithm on top. And this is what I would like to briefly demonstrate. So what I've set up is a table containing movie data. So basically, it's a title and a text. And of course, I also have the embedding vector down here. So we see the structure of the movie table. There are, I guess, 10,000 movies in there. Yeah, slightly. So the next thing I will do is derive that partial similarity matrix. And for that, I created a function which simply returns the top k nearest neighbor for a given query vector. So this is a function I created, and it returns basically the top k nearest neighbors. Now, the second thing I got down here is a procedure that calls that top k nearest neighbor function in a parallel way. And the way I'm using that is by using the map merge operator in SQL script. So this simply takes all my 10,000 movies, kind of splits them into partitions, and calls for each of the partitions in parallel this top k nearest neighbor function. So this is a way, easy way how you can parallelize calls to functions. So let's call that procedure. So now we are essentially running 10,000 top k nearest neighbor queries. And it just took us 2 seconds. And what this returns is the ID of one movie, the ID of the other movie, and then this cosine similarity of these text embedding vectors representing the movie description. So this is a pretty fast way how you can parallelize multiple top k nearest neighbor searches. Now, this is my partial similarity matrix, and I will feed that to a graph procedure, which does community detection. So what you see here is that this matrix is the input parameter of this procedure. This procedure is a graph procedure, it's not a SQL script procedure. So the inline syntax here is basically graph script. And what it's doing, it's generating a graph based on the similarity matrix and then runs the built-in community detection algorithm, and it simply returns the result. And here is how I call that. So first of all, I will generate that partial similarity matrix. I will then feed that similarity matrix into my Louvain community detection algorithm, and then I will output the results. And if I run that, all that is happening on the fly on my 10,000 movies. This is a histogram of the communities along with the number of movies that are assigned to that community. And of course, it also returns for every movie its community label. So now, if you bring that on a visualization, you'll end up with something that you see here on the right-hand side, where the individual colors indicate different communities, and the communities are such that are partitions of the graph, so that there are a lot of edges in between one community or in one community, but there are only few edges between different communities. So that's the whole idea of that Louvain algorithm for clustering. So we do see the individual colors representing the individual clusters. And the nice way about that is because the underlying data structure was a graph, was a network, you can use graph layout algorithms in order to bring your clusters on a UI and do a visualization like I did on the right-hand side. So what I used here was force-based layouting of my graph. So that's a nice way for doing visualizations. So since we are at graphs, and I talked a little bit about the property graph engine, the next topic will be the to-be-released knowledge graph engine. And let's start with a little bit of a motivation, since I expect that most of you are familiar with SQL, familiar with the HANA Cloud Database, familiar with relational. So let's think about creating a knowledge base for movies in SQL. So we start out on the left-hand side. So you see a table for the movies, see a table for the actors, and so you see that green join table in between, which kind of indicates which actor played in which movie. So this is all not a problem of neither for the database nor for the developer. And if you want to run a query like, give me all the movies where Chris played as an actor, this is just two joins. It's not a problem for anyone. So everything's fine. However, what happens if we extend our movie database and, for example, bring in additional table for directors? Again, we would need an additional join table, which joins our movies to our directors. So it starts becoming a little bit more complex, especially if you think about movies, about queries like movies with Chris, directed by Joss. So essentially, you would need to write 4 joins. That's still doable, but you get it. I mean, if your schema grows and you also include, for example, reviewers and reviews and stuff like that into your schema, queries can become more and more complex. In addition, what if you want to extend, for example, the data you store with your movies? Like, for example, you would like to also store the year in which the movie was released. Okay, you need to extend the movie table by an additional column depicted here, the year. Also not a problem unless this really happens frequently, or people would like to bring in very flexible, very dynamically new data into your relational schema. Furthermore, what if there is a remote system which you would like to include in your knowledge base, which, for example, holds information on the production companies of the movies? So here the question is, how do you connect to that remote system? How do you identify the tables which you want to integrate in your knowledge base? Which columns are there? What do they mean? And especially if you want to do right joins and stuff like that, you need to figure out, hey, what are the keys? Do they relate? Can I do a search for ID? And in the end, also, what's the query language of that remote system? So it starts to get a little bit tricky. Now think about a different approach where you basically decompose all your data into triples, into subject, predicate, object triples, like depicted on the left-hand side, where you simply say, 4711 is a movie, and 4711 has the title Tor and stuff like that. So essentially, you decompose your data into atomic entities, you could say. Then adding new entities, for example, adding directives or adding new properties to that type of data store is not a problem at all. But of course, you need to find a way to make keys unique. So in a relational schema, it's pretty much easy to keep a key unique for a table. Since we don't have a table, so we're mixing all the data together in one data structure, we need to think about more globally valid keys. Furthermore, it may be the case that certain columns or certain things are not clear from their semantic perspective. So 4711 has year 2011. What does it mean? So we need a rather richer way to describe it. And finally, if we have a data structure like that, how do we query it? So SQL doesn't seem to be a nice way to work with that data structure. So basically, the solution here is that we use globally valid keys, URIs, with certain prefixes and namespaces to make these keys unique. There is ways to kind of use standard vocabularies to define certain commonly used clauses. For example, what does it mean to be released in a certain year? Stuff like that. And since you guessed that, we're talking about an RDF database, a certain type of knowledge graph technology. The query language that has been established over the recent years for this type of data structures is SPARQL. So this leads me to what we plan to release next year with SAP HANA Cloud, which is the knowledge graph engine. So what we will provide is a native RDF triple store. RDF stands for Resource Description Framework. It's a framework and a specification that is around since nearly 2 decades, which kind of specifies how this type of graph databases are constructed and designed. And in its core, there is that idea of that subject, predicate, object triple. So 7 4 11 is a movie, stuff like that, also depicted here on the right-hand side. We do support importing and exporting, of course, of the most commonly used, or all commonly used RDF file formats. So probably you heard of Turtle or JSON LD, which stands for JSON linked data. So you can import and export them in and out of a HANA Cloud system. Of course, on top of that RDF store, we provide a SPARQL query engine. So I'll cover that in a second. So a way to query and manipulate the data in such an RDF database. And we do support multiple response formats, which is also part of that RDF and SPARQL specification. So of course, we can produce CSV, we can produce JSON, and all that is easy, consumable on the application space. But most interestingly, probably, we do offer full SQL interoperability. So you can run SPARQL queries on your knowledge graph and joining it or adding SQL statements. And this is very, very powerful. I'll cover a little bit of SPARQL, but be advised that this flexibility when it comes to storing data is one benefit of that RDF, of that knowledge graph technology, but there is, of course, a little bit more, which I can't cover today. So, for example, there is the idea of inferencing. That means, for example, if your graph contains triple describing father relationships. So A is the father of B and B is the father of C. A simple example for inferencing would be deriving from the double fatherhood relationship is that A is the grandfather of C. So this is a simple example what you can do with knowledge graph databases in order to derive, in order to infer new relationships, new data. For the SQL developers, for you out there, you may ask, how do I enforce consistency or validity of my data? So if I do have a SQL table, of course, there is a SQL data type assigned to every column. How do I enforce that if I work with RDF triples? There's a way to do that, and the approach, one of the new approaches is called SPARQL, which allows you to define constraints on your triples. So for example, you could say there is a property called year that is assigned to my movies, and it's supposed to be an integer value. And these type of constraints can be formulated in SPARQL and enforced on your RDF, on your knowledge graph. So now, a little bit about SPARQL. I mean, at first glance, it looks a little bit like SQL, but it's really the standard query language for RDF databases. So the standard query languages for these triples that we've just seen. It has a select clause, which is a kind of a projection list. So in this example, I do want to get a movie title and an actor name. It also has a from clause where you can reference what it's called a named graph. You can think of it like a table, something like that. And then there is a where clause, which in the most simple form is just a bunch of triples. It's a pattern which you're searching for in your knowledge graph. So let's quickly break that down here. So this is the first triple in the first line where you say, okay, the variable assigned to movie should be of type movie. And there should be an actor which acted in that very same movie, and so on. So this is how you formulate a pattern that you search for in your data graph. And the way how SPARQL is supported, or one way of how SPARQL is supported or will be supported in HANA Cloud, is by a procedure and a table function. The procedure, the built-in procedure is SPARQL execute. It takes a SPARQL statement or data and allows you to insert the data or a query with that SPARQL query. Also, it allows you or supports other so-called query forms, which we will not cover today, but for example, construct, ask, and describe is also supported via that SPARQL execute. Now, the SQL interoperability that I already briefly mentioned before is provided by that built-in table function called SPARQL table, which can execute a SPARQL select statement. So it's read only, but it returns a table with SQL data types. And from there, you are free to do a join or a SQL-based post-processing or whatever. And let's briefly see how that works in the system. So what I've provided is a knowledge graph containing movie information, of course. That specific graph contains about 500,000 triples derived from 40,000 movies and also including actors and stuff like that. So let's use this built-in SPARQL table function in order to issue a SPARQL query where we say, okay, we are querying that named graph called demo movies. And we are simply, the simple pattern doesn't restrict anything. We are simply extracting every subject, predicate, object triple from that graph. So nothing really exciting, and I guess you can be confused by the URIs or the prefixes or the namespaces here. But simply what we do see is that movie number 12703 is of type movie. So these triples are basically looking the very same. It's the head or only a part of our knowledge graph. Let's do something more exciting. So again, we are querying our movie knowledge graph. And here we say, okay, the variable m is assigned to, we are looking for movies. And for movies in our knowledge graph, we want to get the title. So this is a pattern consisting of two triples. M should be a movie, and M should have a title T. And if we run that query, of course, we see a little bit of what's in the system. These are the movie URIs, and these are the movie titles. Now, let's get all the triples that are there for a movie called The Matrix. And so we see that the movie has a certain budget, it's of type movie, it has a title matrix, it's also assigned to two genres, actions and science fiction and so on. Now think about that query. It's a little bit like, give me everything you know about the movie The Matrix. And this would be already pretty hard to do in SQL, because give me everything would mean in your relational schema, you would know all the possible joins you can leverage in order to find related information for movies. And how do you write in SQL a join all possible joins? So here you start to understand where the power of SPARQL and the power of knowledge graphs may lie. In this case, give me everything you know about the matrix. Now let's extend that a little bit further and search for all actors which played in the movie Matrix. So this also returns a bunch of well-known actors here. So it's just a slightly more complex pattern which we are searching for in our knowledge graph. Now, here is something a little bit more interesting. It's what it's called, or the first part of it is called a quoted triple in the RDS star specification. It is basically a way how you can add properties to your edges. So this is, if you're familiar with property graphs, this would be the way how you can assign properties to your relationships. So what this means here is I'm looking for a triple where a crew member contributed to a movie. So that's my subject. The triple is the subject. And this crew member should contribute to a movie by fulfilling a certain job, which we assign to the variable J. And again, we're looking for all the crew members of the matrix. So what we see here is that for matrix, for example, the music director or music editor was Sigmund Gron. So this is the kind of the result from that query, where we are using a quoted triple in order to understand the jobs assigned to that contribution relationship. Now, there's also the way to do optional matches. So think about left joins in SQL, which allows us to, for example, pull the queries that do have somebody which did the casting for the movie. So for these movies, we have a caster, and for the movie called #horror, nobody did casting, or it's unknown. So this is how you do optional matches. There's also a way to do a basic aggregation in SPARQL. So for example, we can count the number of movies. So Samuel L. Jackson played in 67 movies, and these movies summed up to an overall budget of 4 billion, that is, right? Okay. And as the last query, I want to do a little bit more complex things. I would like to do a join of a SPARQL query and a relational SQL query. So what we will be doing in SPARQL is we will find the movies where Russell Crowe acted in, and we will find the movies where Arnie acted in. And with that result from the knowledge graph, with that result from the SPARQL query, we'll do a join to a movie table in order to obtain additional information. Let me run that first part of the query. So what we do see here is that Robin Hood was a movie where Russell Crowe played in. Here do I see the text or the overview of that movie. And what I joined from my relational table was the text embedding vector for that movie description. Now, finally, with that intermediate result, I can compare the Arnie movies and the Russell movies to each other in order to find which of these movies are most similar to each other. So let's run that query where we're spanning a knowledge graph query and a vector-based search, and we'll find that the Russell Crowe movie, Proof of Life, is most similar to the Arnie movie, True Lies. At least if we are looking at that movie description that I have in my table here. Okay, let's get back to the slides. The primary use case patterns are listed here. And the first one, it is not actually a use case for SAP HANA Cloud knowledge graph engine. But the reason why I listed there is that linked open data projects or initiatives are around since decades. And probably were the most prominent driver for that RDF stack, for the SPARQL query language, and all the related technologies. So linked open data is primarily about the publication of data with the possibility to interlink it. So DBpedia, Wikidata are all projects and applications or systems which leverage these RDF technologies and all provide a SPARQL endpoint. So you can do federation query over different sources of information. If we go from that global, very broad perspective, linked open data, to a more enterprise perspective, we're in the area of actually knowledge graphs, where it is about representing entities and relationships from a certain domain. So, for example, in life sciences, many companies are kind of storing the information about their drugs and the recipes and the experiments and the research in such an RDF database. And by that, they are able to also relate their company internal information, which we keep in their knowledge base, in their knowledge graph, relate that data to public sources like drug base and things of that nature. So these are really company-driven initiatives where standards, query standards, semantic standards, well-known vocabularies do play a role in order to relate company internal information to external information. Of course, GenAI also plays a role why knowledge graph technology has picked up some attention recently. So there is a notion of graph RAG, where you essentially use a knowledge graph system in order to derive more structured context and add it to an LLM prompt. So the picture that you see on the right-hand side is pretty much the same as I showed for the vector-based naive graph approach, you could say, where the only difference is that you're not working with text embeddings, but you rather try to generate a SPARQL query from the user input, from the prompt, and run that SPARQL query against your knowledge base, against your RDF graph, in order to retrieve, let's say, a set of triples which you add as a context to the prompt for the large language model. And finally, certain use case patterns also relate to compliance or to process automation. So think, for example, about governmental processes. So for example, if you apply for child support, for example, the rules may be such that you are only eligible for child support when you have 3 or more children and your income is less than whatever. Now, these type of rules can be very efficiently expressed using SPARQL queries or similar technologies. So there are certain systems that run process automation or compliance checking using that RDF type of data store and using certain query techniques on top of that in order to evaluate, for example, if a certain rule evaluates to true or false. Now, I already mentioned that there is RAG, retrieval augmented generation. You can do it on natural language text using text embeddings, and you can do it on more structured data using knowledge graph technologies. So you may ask, how do the two relate, and which one is better? So I tried to come up with a little bit of an explanation when to use what. So as you probably know, if we are looking at naive RAG or natural language text, and we're using text embeddings, there is usually a kind of a pre-processing step where you rip larger documents into smaller chunks and then doing a vectorization of that, which allows you to run a very effective semantic search on these chunks. And it's working well if your end user queries are rather narrow. That means the information, the context information can be found in a single or in a small set of chunks or documents. The large language model then simply would read these natural language chunks, so to say, and you could think about extracting the facts from this natural language text and then composing an answer which is grounded in the documents. If you're looking for transparency, so would like to prove that the answer provided by the large language model is correct, a large language model can, of course, also return references to the documents and say, okay, my answer is grounded on these three chunks. And if you want to prove that my answer is correct, then you need to read through the chunks and make up your mind. So it's a rather indirect kind of proof and a little bit of indirect transparency, you could say. As an example of which end-user queries might run very well using these text embeddings and these vector-based RAG approaches, think about what did Riker do when Picard was kidnapped by the Borg? So it's obviously a question related to Star Trek. And you would retrieve a couple of TV episode descriptions that kind of match semantically the query, and the large language model is capable of deriving that Riker started a rescue mission. So this works well. On the other hand side, if we're looking at that graph-based RAG, we're much more dealing with structured, linked, and well-described entities and relations, just like we've seen. However, as a pre-processing, of course, you need to create a knowledge graph, which is not a trivial task. You can create such a knowledge graph data structure from structured information like from tables, but also from natural language documents where you have the task to identify named entities like persons and locations and events from these documents, and also the facts that connect these named entities that you find in the document and store them in a knowledge graph database. Now, knowledge graph technology, SPARQL, as we've seen, is very efficient when you want to retrieve context that is spread across multiple sources. So since your knowledge graph is a kind of a central way how you integrate information from different sources, and you have centralized that information, you can ask something like, give me everything for the movie Matrix. And this is one of the sweet spots for graph-based RAG approaches. Now, since you would simply add a bunch of triples to the context and hand it over to the large language model, you could think about the large language model simply aggregating the facts, the triples, and compose a natural language response. The transparency in that case is pretty straightforward, since you can always point to the set of triples that kind of make up the answer by the LLM. So it's direct lineage, you could say. You can even come up with a visualization of that partial graph you gave to the large language model and really see, okay, here's the connection, here's the reason why the large language model provided a certain answer. So This approach, GraphRag, using knowledge graph technology, is very appropriate for very broad or very complex queries, like the one depicted here below, where you ask which actors played in science fiction as well as Western movies, but never worked together. So this is incredibly hard if you want to derive suitable context or answer that query if you just have natural language text, documents, and text embeddings, because you would essentially need to scan, so to say, nearly all of your documents, nearly all of your descriptions in order to find that answer here. But if you kind of condensed all your information in a movie knowledge base, these type of queries become very easy to answer. Having said that, it should be clear that if we're looking into retrieval augmented generation for GenAI workflows, the question is not what is better, vector engine or knowledge graph? What is better, vector-based RAG or graph-based RAG? It's essentially, in the end, it will be use case dependent, and most probably will end up in a system that supports multiple of these, let's say, RAG techniques, where you essentially have a generative AI app which takes an end user prompt, generates various queries, be it SQL, be it SPARQL, be it via text embedding, be it via full text search, and searching various sources of information at once, and then fusing the results, maybe re-ranking the results in terms of identifying the most relevant pieces of information, which are then handed over to the large language model in order to provide the best answer to the end user prompt. So that's all I have for today. Before we go over to Q&A, I'd like to thank you for your time and hope it was interesting.
Thank you so much. It was really interesting. I was listening myself, obviously. I really, really loved it, and especially how you also talked about RAG and GraphRag, because GraphRag is kind of what interests me a lot, right? I focus more on AI, and we also had a GraphRag session a couple of weeks ago from Tahir Ögel, which was also really cool. And I just can't wait to try out our knowledge graph and do a GraphRag case. Have you tried it out, actually? I don't know how much you get to play with your own technology.
Yeah, well, partially. I mean, I've been playing that with that, of course, and also using it, looking at different techniques, and of course, what you find out, they all got their benefits and their limitations.
Yeah.
And if you switch the context or the application frequently, you find yourself trying a lot of approaches. Yeah.
Yeah, for sure. I also want to try out like a hybrid approach of like normal RAG and GraphRag and stuff. We have a question in the chat. I'm just going to read it out and then you can answer it. Is there a simple way to populate your existing SAP data, for example, S4 HANA data, business partners, contacts in the knowledge graph, so that you can then enrich and or create the relationships with open data?
Yeah, I mean that question has basically two steps. So if you think about you have your enterprise data stored in tables, of course there are approaches how to translate them into that knowledge graph RDF format. There are Python libraries out there. You can also go and write SQL queries in order to populate a knowledge graph. There are ways to do that. There is no one size-fits-all approach for that, but we at SAP are looking at techniques that makes that easier for developers to provide or to translate from one of the formats into the other. The second part of the question, however, is how do you relate to external sources? And this is a question about the keys and about URIs and being able to relate your, let's say, business partner in your ERP system, which just have an internal SAP key, to something out in a Wikipedia, for example, where
Mm-hmm.
company might have a different URI. So there are
Mm-hmm.
mapping services which allow you to map from your local domain to other well-known domains, but this
Oh.
is for sure not a trivial task. But there are ways to do that. There are services out there which do the key mapping, so to say.
Mm-hmm.
It's doable.
So what if I, for example, have a knowledge graph already and I want to add like a new connection or a new entity? Is that something you can add after, or is it always you have to kind of set up your structure beforehand?
Yeah, that's definitely one big pro of that knowledge graph technology, that it's designed in a flexible way so you can add
Mm-hmm.
later on for sure. One thing I didn't cover is vocabularies and
Mm-hmm.
OWL in specific, which is a way to describe the metadata, so to say. So which entities, which classes do you have in there, which
Mm-hmm.
relationships are allowed. And usually that vocabulary and the data go hand in hand, but it is not a prerequisite to have that vocabulary, that metadata in place when you start populating your knowledge graph. So short answer is it's perfectly fine to start with a small knowledge graph and add over time more and more entities,
Mm-hmm.
classes, and relationships to it. But you need to make sure that you stay in control and you have some metadata layer
Mm-hmm.
sooner or later, which help you to identify what you already put in
Yeah.
your knowledge graph.
Okay. Um, I think you already actually compared the graph engine that we had in HANA before and now the knowledge graph that we're adding. But can you just summarize one more time, like why there was a need for the knowledge graph?
Yeah, I mean, the use cases for the property graph and the knowledge graph are a little bit overlapping. But let's say on an extreme way, if you have relational data and you would just like in a very easy way, without replicating data, use built-in graph algorithms, then the property graph engine is the way to go.
Mm-hmm.
Think more in terms of algorithms, finding shortest path, doing community
Mm-hmm.
detection and stuff like that on primarily relational data where the properties are the columns in your table. On
Mm-hmm.
the other hand side, as I mentioned, that knowledge graph is something that grows over time, does have certain standards with it when it comes to vocabulary. So it makes it more easy to describe the data semantically. So there are better tools to do that compared to relational. There are standards like the SPARQL query language, which allow you to do federation to other knowledge graph data sources. And it's rather, when you think about a query, it's rather pattern matching. It's
Mm-hmm.
not finding shortest path and doing community detection.
Okay.
It is rather pattern matching, but with clear semantics and with a very flexible data store.
Okay. Thank you. It's actually all my questions now. So if anyone still has questions, you have 3 minutes. Put it in the chat. Maybe you have a chance that I can still ask it. Otherwise, I have one more question. Again, obviously, regarding the knowledge graph and the knowledge graph engine. And I know that when we saw it in the keynote, that a couple of people approached me after and they asked me, why do we have a knowledge graph and a knowledge graph engine? Like, kind of what's the
Ah.
difference? And I think the word engine kind of gives it away, but
Mm.
maybe you can elaborate on that a little bit.
Yeah. I mean, SAP is not always the best company when it comes to clear product names, stuff like that. But the answer is very simple. Simple. SAP Knowledge Graph is data. It is a knowledge graph describing SAP objects like ABAP tables, CDS views, APIs, and the like. So it's data. The SAP HANA Knowledge Graph Engine is just a piece of technology, a store and a query engine. But obviously, once we publish the SAP Knowledge Graph, it will run in the HANA Cloud Knowledge Graph Engine. So think of it, data versus technology, knowledge graph engine.
Okay, awesome. Thank you so much. With that, we're already out of time. Thank you so much for your time. I really enjoyed it. To the audience, again, make sure you join the Devtoberfest group in the SAP community and you catch all the great sessions that we also have next week. Obviously, the entire week, but especially the Mad Thursdays. There is a lot of cool content next week as well. And I'm going to post the validation tutorial in the session description wherever it shows up in a bit. And that's how you can actually get points for watching the session as well. I really enjoyed it. I hope you did too. And yeah, see you next week, everyone.
Thanks. Bye-bye.
Bye.